From yesterday, actually the lab that I gave you for today, I start off with the nutrition facts label of your food item. So you need to know what your food item, the nutrition facts are. So on this food item, like marshmallows, it tells you right there. So this morning I got some peanuts. Peanuts work the best because they're easy to place on the apparatus to burn. So the nutrition facts label for peanuts, a serving size, you need to write that down. That's important from your nutrition facts label. You need to know what a serving size is. You need to know the calories per serving size. So for the peanuts, it's 170. Now that's a conversion factor. That is the serving size equivalent to the calories is a conversion factor. So 30 grams is going to give you 170 calories. Does everybody understand? Alright, so then you're going to set up the apparatus. You're going to burn the peanut or burn the food item. You're going to measure the mass of the peanut before you heat it, the food item before you heat it, and then after you heat it. That's important to know. You need to know the before and the after. So in this situation, you have 0.3 grams of energy produced in the peanut. This is true when you consume food. You eat food and then you go to the bathroom, you poop out the waste. So the waste here would be the 0.6. Everybody see that? Because 0.6 plus 0.3 is 9. Everybody see that? So that's waste. You don't get energy from waste. You poop that out. All right. So up here, one small cal is the amount of energy needed to raise 1 gram of H2O 1 degree Celsius. That's the standard definition for calories. 1 big C is equal to 1,000 small C's. Why don't they put 170,000 on your food items? That would kind of freak you out. You'd be like, 170,000 calories? I need to stop eating. That would be bad. Don't do that. All right, so up here, we're taking our 0.3, right? That's the energy that we had when we burned the peanut. And then we're going to multiply it times our conversion factor to see how much energy was in that 0.3. So we take 0.3 times 170 divided by 30, we end up getting 1.7. So we have like 1.7 times 1,000 is 1,700 calories. This is the theoretical prediction. This is a theoretical prediction. All right, so now when you do this by water, right, you're going to fill the can with 200 milliliters of H2O, right? And then you're going to burn the food item. You're going to measure the mass before and after the burn. So we're saying here that 0.3 grams of energy is produced there. Now the initial temperature of the water, you need to measure that. This is by water, so you're going to do, let's say it's 23 degrees Celsius, that's what the thermometer says. Then you got the final temperature is 33. So does everybody see you got a 10-degree temperature difference? Now you put 200 milliliters of water in the can, so you change that 200 milliliters by 10 degrees. Does everybody see how you're measuring the temperature of the water? Does everybody see that? So we go down to our formula here. Q equals 1 cal per gram. This is a conversion factor, or a standard. And then we're going to multiply it times the mass of H2O, which would be 200 grams, then times 10 degrees Celsius, giving us 2,000 calories, right? So this 2,000 comes from our calculation. Now we're going to take the 0.3 grams is we're saying it's 2,000. We're saying we produced 2,000 calories based on our experiment. So we take our 2,000 divided by 1,700. So we've got about 17% error associated with our lab, right? Everybody see that? So this is where your error can come in. Did the water heat it correctly? We're saying up here that you should theoretically get this number, but you might not. When you measure the temperature change, you might have a problem there. All right, so over here, this is by ice. You're going to fill the can with ice. There's 2 ways of doing it. You can do by water or by ice. So we fill it with ice. And then we burn the food, and we measure the mass before and after. Let's say it's 0.3 burned. Then you're going to pour the water that's ice that's melted into a graduated cylinder. Let's say it's 35 milliliters, right? So then we have the mass of the peanut correction, the mass of the water, that would be 35, times 80. This is another standard that is used to help us calculate the calories here. So we take 35 times 80, that gives us 2,800. We take our 2,800 divided by 1,700, and we got 160 or 60% error. So whichever amount that you get, like if yours is not 0.3, let's say it's 0.2, and you just put 0.2 here times 170 divided by 30, that'll tell you what your theoretical is. Then that's how you compare everything to your theoretical. And then from this you can determine which one worked better. So which of these two work better, example 1 or example 2? Yeah, example 1 had less error. Example 1 had 17% error. This one has 60% error. So that's kind of what you're doing. You're trying to compare, which two systems are working better. Now, one might be more difficult to do, so you might choose the one that has more error. It really depends on where you are in the workplace. People will tend to choose the one that has less error just because people don't like error. People don't like being wrong. Kind of freaks them out. Yeah, it should hold 200. They'll burn all the way to completion. Whereas like marshmallow and Rice Krispie treats.
Rice Krispie treats,
Check out the peanut. It's a champion. Doesn't want to stay lit for very long. Kind of look like it close out. Marshmallow.
You missed Gary. Very bad.
You gotta burn for a little bit. So now what I would do is. So I don't remember from last year which one works better. I think the ice one works better, but I don't,
My face is prepped.
You did what? Oh, it looks like it's
It
burning a
won't
little
like
bit.
light. It'll just burn.
Where's this 2,000 calories?
You might want to try a smaller piece. Claire's gonna go for it.
Stop,
This
Mr.
cookie is going to
Sonic.
burn.
He said they put you 1,000 calories, it would scare you, so I think it's...
So what did I write?
Is making videos your hobby?
It is.
Did you have your
Story.
own YouTube channel?
I do.
I mean, that's just going to burn forever. That's whatever.
18 calories?
Looks like the cookie's winning.
Ah.
You want to fill your can to the top. The more ice, the better.
My finger's bleeding. It's a cinnamon gum.
Cinnamon, is it sugarless?
I don't know.
If it's Orbit, it's probably sugarless, so you're probably not going to have too many calories in it. It's sugarless. Burnt chip after you burn it. Now, you got your 200 milliliters of water in there, right? And you need a thermometer in there so you know the before and after temperature. Because you didn't have the thermometer in there, you're going to have to do it over because you don't see the temperature change.
Who did that? Why would you do that, bro? Why would you do that, bro?
Try to put it underneath. There you go. It should catch on fire and burn really well. Just about got it. I think you pull your match away. Nice job. Now, did you write down the temperature of the? Oh, you don't need the temperature of this. You're just melting the ice. So once this is done, you're going to pour off the liquid, see how much ice is melted. Multiply that times what? The water you guys need. Excellent. Did you measure the initial temperature?
Ow! Yeah.
Good. See how it's increasing the temperature? What was your initial temperature?
23.
Looks like you're at 25 right now. 126. It's like you're 27.
God. You busted it. Busted it.
Busted a fat nut.
God darn it, man.
Still going.
Can we just do a marshmallow? See those marshmallows over there?
It's like you're around.
So much easier.
Started
Man.
I'm supposed to put this on this.
7,
Yeah, I got
maybe
it.
How was a
28.
nut supposed to go on something that's sharp? Makes no sense.
I would give it about 5 or 6 seconds.
So we like the nut on fire.
Yeah.
It's like next 10 fire.
So what goes in here?
Ew, is it supposed to make that noise? It's sizzling.
Yeah.
It's
the
not
sugar.
catching on fire.
Fire. You
The
said
sugar's
sugar
in the
burns.
star, but it should
It's not though. Explain science. Here, I'll light another one.
It's gonna burn me.
Yeah, you want to get it underneath of the food item so it'll flame up.
Alright. How much water are you putting in? Okay, so
It's caught there. That's good. That's good. So then you're gonna let it melt the ice and then measure the mass of the water. Now you're gonna take that volume multiplied times what?
The mass?
Times the standard, which would be 80. 80 calories is the amount of energy it takes to melt ice. So it'd be a constant error. Here you get like 70% error. So you can see you're proving that this one was working better. This one's providing better results than this one. So that's all you got to do in your write-up is say that. You got full credit. Make sense? Now what you're going to do is you're going to record the temperature. Did you get the initial temperature? 23 degrees. When it's final, write that down. Liquid, and then you're going to measure the liquid.